So we are going to start with a distinguished paper, which will be presented by Alexandre. And for some reason, there are no slides anymore. So what happened here?
No, they will come up, hopefully.
Okay, good. Alexandre, the floor is yours.
So hi, everyone. So my name is Alexandre Moine. I'm a postdoc at NYU. And today I'm going to present joint work with Sam Westrick and Tassarotti. And the paper is titled All for One and One for All, Program Logics for Exploiting Internal Determinism in Parallel Programs. So it's still early in the morning. Let's see an example. This is a Dumas function that takes as parameter an integer n, and then allocates a reference r, initialized to 0, and then in parallel adds to r 18, 2 and 42. Let's say the addition is atomic here. And then after this parallel phase, the program asserts that the content of R is equal to n. What can we say about this program? Well, first of all, it's safe if and only if n is equal to 1844. Otherwise, the assertion here will fail and the program will crash. The other thing we can say is that this behavior is difficult to verify in separation logic. Indeed, you have a pointer, R, that is being written to by two concurrent tasks. Let me show you the proof. So it's the same program with more space. And in separation logic, first, when we allocate this pointer here, we get a points to assertion. So we have that R points to 0. Now we face a par. So what is a par, rule of separation logic? Well, it's this one. To verify par ELER, you have to separate, this is a separation logic, to separate your precondition in two pieces, one that will go to the left side and one that will go to the right side. However, here we have an issue because we have a single points to assertion, but we will need it in the two sides, so we are a bit stuck. We cannot split it. So of course, concurrent separation logic is powerful enough to verify this example, but in this case, you need heavy machinery, you need invariance, you need ghost state. There is no need to understand anything here. Just want to display that this proof is difficult. And it's difficult, well, for a good reason. It's painful because this proof verifies that every possible interleaving or ordering is correct. So either, so it verifies that the prime is correct, even if the addition of 18, 2 happens before 42 or the other way around. But one observation we can make here is that the order of the addition does not matter. Additions commute. So this proof is a bit too difficult for its own good. The remark we can do is that many programs are like Dumas, or what we call internally deterministic. It's a terminology coined by Blalock et al. It means that every action of every parallel task is deterministic with respect to the interleaving. That means that the interleaving cannot be observed by the program. And this is a very cool property to have because it means that you have what we call in the paper schedule-independent safety. So this property says that if one execution of the program is safe and terminates, then every execution is safe. And this property is very cool because it means that proofs become very easy. You just have to verify that one interleaving is correct to deduce that they are all correct. And this is, of course, the Three Musketeers motto, one for all and all for one. And it also means that you can also test a concurrent program efficiently. You just run the program once, and if it terminates, you know that every other interleaving will also be correct. So to draw things here, the general way to verify that a program is correct is to use separation logic. But here what we propose is a new recipe for verifying internally deterministic programs. So we propose to split the safety proof in two sub-goals. The first one is to prove schedule-independent safety, and the second one is to prove that one interleaving is correct and terminates. In order to prove these two goals, we have two program logics. The first one is called Musketeer, and the second one is called Angelic. Then the question, of course, is wait. Are you suggesting that we do two manual proof instead of one? And of course, the answer is no, because we prove that you can verify schedule-independent safety with a type system. So we also propose several case studies, including primitives from this article from Blalock et al. And Musketeer, Angelic, mini-dead this type system, and the case studies are mechanized in a rock prover on top of the IRIS framework. So here I will first present Musketeer and then present Angelic. So this Musketeer triples. So Musketeer looks like a standard separation logic. You have a triple here, an expression being verified, the precondition P and the postcondition Q, except that the postcondition is parameterized by the return value, V, and a ghost return value. I will say more in a few slides. Such a triple guarantees a hyper property, a for all hyper property that is a bit verbose, so brace yourself. It says that if one execution of E is safe and terminates from a heap satisfying P, then every execution of E is safe starting from a heap satisfying P, and all terminating executions will end on a heap satisfying Q. Well, the important thing to understand is that if we trivialize P and Q, we get a soundness theorem that says that if we are able to verify the program E, then we know that E satisfies schedule-independent safety. What are the rules of this program logic? Well, Musketeer is almost like a standard separation logic, so you have points to assertions, higher order ghost state, invariance, and almost every separation logic rule. So in particular, we have a rule for creating a points to assertion. So if we do a ref on V, we have a points to on V. Then we have a rule for loading a location. If L points to V and we get L, we have a value V, and L still points to V. And we also have a rule to set the content of location. If L points to V, and we set it to V prime, we have L points to V prime. And we even have a standard par rule. However, there are two key differences with standard separation logic. The first one is the assert primitive, and the second one is how we deal with the existential quantification. So, the reasoning rule for assert. The primitive assert V is safe if and only if V is equal to true. Otherwise, the program will crash. However, Musketeer offers the following reasoning rule for assert. It says that you can verify assert V without precondition. So you can apply this rule even if V is false or even if V is equal to 42. And you deduce in the postcondition that V is equal to true. So obviously this rule does not guarantee safety, but it does guarantee Musketeer's motto. That is, if one execution of say assert V is safe and terminate, then every execution of is safe. Indeed, if one execution of assert V is safe, it means that V is equal to true, and then if V is equal to true, every execution of assert true is safe. And then also be reassured, here we have assert V for a value, but we have a bind rule, so we can reason on assert E for an arbitrary expression E. Now, something a bit more tricky, the existential quantification. This is a small variant of the Dumas program that does not satisfy schedule-independent safety. We have a reference R, and then this program in parallel says R to 1 or to 2, and then assert that the content of R is equal to 1. So of course this program might fail because it may observe the scheduling, that is if the left task here execute before the right task, or they will then be equal to 2 and the assert will fail. So Musketeer is a sound logic, so where does the proof fail? So we can allocate the points to, we have invariance, as I said, so we can allocate the invariant, even verify the two parallel sets. But then you are up to a point when you need to eliminate the existential quantification. That is, you are in this state, you know that there exists an n such that R points to n, and then you want to verify E for any possible witness of the existential quantification. And Musketeer does not allow you to do that. So that where the proof fails, we do not have a rule to eliminate the existential. And this is for a good reason here, because the existential here hides the interleaving. It hides which thread won the race. So Musketeer prevents from eliminating arbitrary existential quantifications, but when we know that the existential quantification was chosen deterministically, we have a solution, and it's this ghost return value. So here, to explain the ghost return value, let me first present how we reason about a let binding in separation logic. So this is a standard let rule for separation logic. To verify let x equal E1 in E2 under the precondition P, you first verify E1 under P, and you have to give a postcondition Q prime. And then you have to verify E2 under the precondition that there exists some value that satisfies this postcondition Q prime, and you replace in E, X, the binding, with the value V. And most of the time, the existential quantification is used to transmit information from this postcondition to this precondition. So you often have an existential quantification there. And in Musketeer, we allow for that somehow with this ghost return value. So both conditions now takes two arguments, the physical and the ghost return value, and you can think of this ghost return value as an existential quantification in front of Q prime. So this is the rule in Musketeer. You have to provide a postcondition that will hold for some value and some ghost return value, and then you get to assume that there exists a witness of this ghost return value while reasoning on E2. And then you have to, when you reach a value, you have to provide a ghost return value. That can really be anything. All right, so why does Musketeer work? I will not show you the proof, but some intuition. The intuition of Musketeer is that assertion of Musketeers do not describe one, but two executions. You have the left execution and the right one. So assertions are defined, are parameterized by a Boolean indicating either the left-hand side or the right-hand side. For example, the points 2 of Musketeer is defined as a function that takes a side, and if this side is left, you return the left points 2, and if it's right, you return the right points 2. And you can see here the issue with the existential. The existential quantification of Musketeer here is defined as, well, give me a side, and I will guarantee a witness and guarantee then the property. But the witness can depend on the side. So it means that in Musketeer, when we have an existential quantification, actually you have two witnesses underneath. So that's why you cannot open the existential. Then, to a Musketeer triple, intuitively, is defined like this. It's a nested weakest precondition. So you suppose that the precondition holds for the left-hand side. You verify E. Then you have the postcondition for the left-hand side, and then you have a weakest precondition for the right-hand side, so you get the precondition for the right-hand side, and you have to deduce the postcondition for the right-hand side. This WPR for the right-hand side is a standard weakest precondition, and this one on the left-hand side is a weakest precondition that does not guarantee safety, but is otherwise entirely standard. So this is, of course, awful to read, and if you read the paper, we have a nice API for this beast that we call chain triples. Back to this Dumas example. So this Dumas example in the introduction satisfies scheduling-dependent safety, so we can actually verify that this program is correct. Well, satisfies scheduling-dependent safety, so we establish this triple that says that for any n, Dumas n satisfies scheduling-dependent safety. The proof is not that easy. You have to use invariants, you have to use these ghost return values, but the observation is that this proof can be obtained with a type system. The overall idea here to guarantee scheduling-dependent safety is that you just need to ensure that there is no read during the concurrent write phase. So we designed a small type system to do that. This type system is called minidet. So it's an affine type system. So you have here a typing judgment, you have the entry typing environment, the output typing environment, the expression, and the type. So it supports primitive notion of exclusive and fractional ownerships, and we extend it with some primitives from this Blalock et al. Paper. We have a Sandler theorem for this type system. If you're able to give a type to E, you know that E satisfies scheduling-dependent safety, and the proof is mechanized, and it's done with a logical relation in Musketeer, meaning that for every syntactical type derivation, we associate a triple in Musketeer. And we can type check Dumas, spare you the details, but we can give to Dumas the type into units, so to show that Dumas indeed satisfies scheduling-independent safety. All right, now that we know that Dumas satisfies scheduling-independent safety, we can use this property, and now we know that it suffices to verify that one interleaving is safe and terminates to deduce that every interleaving is safe, and then it means that we can get an interleaving, pick an interleaving to verify. So for that, we introduce a new program logic called Angelic. It looks like that. You have a precondition, you have this run modality that looks like a weakest precondition, an expression, and a postcondition. And the Sandler theorem says that if you are able to verify the program E, then you know that one execution of E is safe and terminates. Again, what are the rules of this separation logic? It's again almost like a standard separation logic. You manipulate points to assertion, and it supports ghost state without step indexing in order to guarantee termination. Then these are the rules of Angelic. So you have the standard rule for ref, get, set, and also for assert. So this time for assert, you have to prove that one execution is safe and terminates. So you have to prove that the value is indeed equal to true. Then the fun part of Angelic is that it allows you to pick any interleaving to verify. So for example, to verify run of par EL, you can first verify the left-hand side and then verify the right-hand side. So if I draw a diagram, you can do 1, 2, left-hand side, and then 3, 4 for the right-hand side. But also you can pick the other interleaving. So to do first the right-hand side here, ER, and then the left-hand side, EL. So do 1, 2, 3, 4. But Angelic really allows you for picking any possible interleaving. So for example, you can do 1, 2, and then 3, 4. And we have some general rules for doing that. So to select an interleaving in Angelic, we introduce two new assertions. The first one is yielded by E to set that the task pi is currently executing E. And then we have an opaque goal that I describe with this Gothic goal here. So the rule for fork, so to verify run of par EL, you get to assume two task identifiers, pi L and pi R. You get to suppose that pi L executes EL and pi R executes ER. And then you get something like a continuation that says that when pi L will reach a value VL, pi R a value VR, and the post-condition Q holds, then you can prove this opaque goal. And then your goal is this opaque thing go. Then of course you're a bit stuck here. And so we provide a resume rule that allows you to resume the verification of any task. So if you know that task pi is executing E, you can resume the proof and reduce the goal to proving a run of E. And then in the post condition, you get to know that pi reached a value V. All right, so the two interleavings, these two rules allow you to really execute fully one task or the other, but we also have a rule to yield and stop the verification at any point in the proof. So for if our goal is run E, we can at any time suppose a new task identifier pi, and suppose that pi executing E, that when pi will reach a value V and the post condition hold, we have the goal, and we just need now to prove the goal, and we can switch to another task. All right, with all of that, we can finally do our proof of Dumas. So, of course, here you have to call Dumas with the correct argument, 1844. So we first allocate the points to assertion, then we face a par, followed by an assertion. So we use the bind rule to focus on the par. Then we face a par of add R18.2 and add R42. And then we can choose the one to verify first. Let's take the left-hand side. So we verify first the addition of 18.2. It updates the points to assertion, as you can guess. Then we verify the addition of 42. It again updates the points to assertion. And then, trust me, the rest of the proof goes through. Here, the observation is that we really made only elementary steps. And in particular, we did not need at any time to split the context. So it can likely be automated. We also have a termination proof here, but because the problem is not recursive, well, it's manageable. Okay, at the conclusion, I just presented all for one and one for all, program logics for exploiting internal determinism in parallel programs. The key ingredients were schedule-independent safety, so this property that says that if one execution is safe and terminates, every execution is safe. We have Musketeer, which is a semantic model that captures schedule-independent safety, and we have Angelic, a program logic for verifying that one interleaving is safe and terminates. We have several case studies, so this affine type system with Primitive, Pomblelot et al., and everything is mechanized. As future work, you can perhaps guess it, we're interested into schedule-independent termination. That is the property, if one execution is safe and terminates, every execution is safe and terminates. But termination is a liveness property, and these kind of things are difficult to verify in separation logic. Thank you, I'm ready for questions.
Thanks to Alexandre for the talk. Any questions? Thibault?
Thank you for the great talk. So I was wondering, on your two motivating examples, one, you add and it works, it's schedule independent. The other one, you set and it doesn't. And it seems really related to commutativity. Yes. So I'm wondering if commutativity appears explicitly in the logic and in the type system, or if somehow it's a consequence.
Somehow it's a consequence. Really, the logic integrates the notion of commutativity. And does not show in the proof, interestingly. In the type system a little bit, because you have to show that addition commute, for example. So in order to prove that the addition satisfies independent safety, you have to show that it may commute with any other addition.
There in the back.
Thank you for the talk. So the type system that you presented, does it also come with a traditional safety result? Because the schedule-independent safety, to me, doesn't seem to imply that, of course, the program actually executes correctly, right?
Yeah, right. So I think it will. It can come with a safety proof, but we do not provide this safety proof for the type system.
Right, but so I'm imagining if I have my own type system where I want to do, for example, a traditional safety property and also your schedule independence property, do I then have a logical relation and a semantic proof that has two kinds of triples? Could you combine these things in some way?
If you already guarantee safety, you have really no need for schedule independent safety. Because the whole point of schedule independent safety is to easily prove safety.
Sure, but what if I have a type system that says safety up to assertions, for example?
So if you want to do that, yes, you will have two triples, I think.
Okay, thank you.
More questions? Here in the second row, please.
Hi, thanks for the talk. Very interesting. I wonder if you need some fairness assumption to guarantee the result.
We have no fairness assumption for now.
Here, first row.
Yeah, and so regarding again the first logic and type system, do you support non-determinism in branching? That is, in one you have a conditional, and in one execution you take the first branch, and in the other execution you take the other branch.
We do support it, not at the musketeer level, but at this chain triple level. You can actually verify that as long as you guarantee schedule independent safety. Yes.
But would the type system mean that, I mean, to...
So not at the type system level.
Okay.
So, yeah.
Thank you.
I also have a question myself. So I would expect that in some cases you don't really want to have non-determinism up to equality, but up to some equivalence relation. So for example, whenever you're dealing with, let's say, like data structures like sets or maps, then they're represented on some kind of a tree, and then depending on the order, you might get a physically different representation, but something that is logically the same. Does your work support that?
Yes. I think yes.
Can you say a bit about how?
Okay, yeah. If you want to give a musketeer interface, you will have to prove this. You can just prove the chain triple, so this nested weakest precondition. So you have to express the relationship between the two representation predicates at this level. So it does not support the reasoning at the musketeer level, but underneath you can do a semantic proof.
Okay, so you really have to unfold the definition of this WP thing and then reason explicitly.
I think for now, yeah.
Do you think there is any hope of providing like high-level rules?
Yes, I hope, but I don't know yet.
Okay. Any more questions? Okay, then I have one more. So suppose you have like you have a musketeer and an angelic proof. Then from this together you get like some kind of like safety at the meta level.
Yes.
But do these two things together imply like an ordinary iris WP?
Yes. In the proof, like when you extract the standard, when you extract the meta theorem in the end, you actually go through a standard iris weakest precondition.
So maybe let me rephrase. So suppose you have a program where some part is makes use of is internally non-deterministic, and the other does do all kinds of weird stuff that wouldn't fit.
Oh yeah, no.
Can you then verify that part, the difficult part, using like the standard iris invariance, and the other part using your?
No, we don't support that yet.
Any hope?
Yes, again, very hopeful, but yeah, I'm not sure.
So you don't have a concrete idea yet?
No.
Okay, sounds like a nice future work. I think the next speaker can set up, and if in the meantime there is a very short question, feel free to. Okay. Okay, I think we can thank Alexandre and